All right, so when we were looking at our data that we'll be examining in this lab, I talked a little bit about what super consistent regressions are, and recall that that just happens if you take two non-stationary time series and try to regress them on one another. You'll get something that appears to be statistically significant with a t-test, but the relationship is probably not meaningful. So just as a kind of a cheat sheet for you, this is sort of the workflow that you should be using anytime you're going to start out doing a kind of time series econometric based exercise. The first question you'll always ask is, are my data stationary? And there are statistical tests you can use to check that. If the answer is yes, they're stationary, then you can choose a regression model with prices and levels. This is quite rare, actually. You'll much more often find that your prices are non-stationary in my albeit limited experience. So if you do your stationarity test and you find that your data are not stationary, usually choosing a regression model where you're using first differences of logged prices will correct the problem. Okay, so that's Introduction to Time Series Econometrics, Stage 1 for you. Okay, now next we're going to skip ahead to the kind of time series model that we'll be using in our example. So I'm going to skip over here to Chapter 19, which is the second appendix. And here's a little reminder to double check whether your series are integrated or not. What we're going to be using is this ARP regression model. Okay, it's a good time to talk a little bit about what we call the efficient market hypothesis, because let me skip back just to motivate this to our data. We talked about how if we're going to be trying to forecast percent returns to make money trading, it's going to be pretty difficult when these are the kind of percent return evolution from day to day that we could expect, because it looks pretty unpredictable. And this unpredictability in percent changes is actually consistent with the efficient market hypothesis. The efficient market hypothesis says basically that you're not going to be able to use past prices or past returns or any kind of information known at time t to predict returns at time t plus 1. Another way to say that is any information that would be useful for forecasting or for information about what the right price should be for this market is already incorporated into current prices. And so forecasting tomorrow's price is going to be a futile venture. So there's been a lot of academic debate about whether markets are truly efficient, but it's probably safe to say that if they are efficient, they're not inefficient if they are inefficient, they're probably not inefficient for very long. Because as soon as someone discovers, oh, the price is too low, or oh, the price is too high, then they have a very strong financial incentive to go into the market and buy if they know the price should be higher, or sell if they know that the price should be lower. And so this kind of disparity between what the price is and what the price should be gets basically arbitraged away by traders who are informed. That's the theory anyway. And that is the theory that basically explains why we would see commodity markets or other kind of assets that are traded frequently reveal percent returns that look like this. Because, after all, if it were easy to forecast percent changes, then we could all be really rich. Okay, so is there any hope for us in this effort to forecast prices? Well, sometimes it turns out that there is something called autocorrelation in returns, and that just means that tomorrow's returns are maybe not predictably forecastable with today's returns, but maybe they're kind of correlated to today's returns, or today's returns and yesterday's returns and the day before's returns. If that's true, then we could just simply check if there is correlation between today's returns and past returns. And we could do this pretty simply in Excel. We're not going to do this part, but if you wanted to see if there's autocorrelation, you generate your return series and then lags of the return series. We will do that part because we'll need it for our ARP regression model. But then if you go and you just calculate using Excel the correlation between columns C, D, and E, you'll be able to find if there's significant correlation or not. In this example, the correlations are pretty low and maybe probably not statistically significant. So if you don't find heavy evidence of autocorrelation, then your autoregressive model is probably not going to be great as a forecasting tool, but we'll go through the motions and see how it's done anyway. So here's what the ARP model looks like. It simply says that we're going to try to forecast tomorrow's returns, that's RT plus 1, by this linear regression that includes the previous P returns. So forecast tomorrow's returns with today's returns, yesterday's returns, and several days before. So the P is obviously the number of lagged returns that we include in our regression model. Now, so that means that to do this, we're going to have to decide what is going to be the order of our ARP model, or what is P going to be? How many lags are we going to include? And oftentimes that's done usually with something called the AIC, Aki-Iki Information Criterion, or BIC, Bayesian Information Criterion. And that would basically just try out a bunch of different models. So lag 1, lag 2, lag 3, lag 4, lag 5, all the way up to some maximum, and tell you which one kind of fits the best. And then you select your lag based on that. We're going to shortcut that part and just do a lag 3 model.